Hi everyone, my name is Taegyoung Lee and I am from HKST in Hong Kong. My talk is fitting a graph to one-dimensional data. This is joint work with Siu-Wing, Cheng, and Otfried. Many data sets can be represented as point set in d-dimensional space. With this data set, we can get a proximity graph. Proximity graph is a graph that connects two vertices by an edge if vertices have relevance, and the vertices are points in the dimensional space. The edge weight between vertices indicates how strong relevance between two vertices. And proximity graph is useful in classification, clustering, and regression. This is an example of clustering by using a proximity graph. Given data, we can construct a proximity graph, and then we can get clusters using the proximity graph. We use a graph proposed in ISMA 2009 because it is probably sparse and it offers good performance. To get a proximity graph, given n points in the dimensional space, we have to determine the weight of the edges connecting two points. For each point pi, there is a vector vi. So in this example, vector vi is a vector is made by other 5 vectors with weighted edge. And let vi be the norm of vector vi. The weights are chosen so as to minimize the sum of vi square. If we make the weight of every edge 0, the sum of vi square is minimized. To prevent such a trivial solution, the weight for each point add up to at least 1. The optimal weight can be computed by quadratic programming. A quadratic programming problem with n variables can be solved in nearly big O n cubed times in the worst case. In our case, there are about n square variables, which give nearly big O n to the 6th time. It is slow even for moderately large number of variables. Therefore, our goal is to design an algorithm that is significantly faster than quadratic programming. One-dimensional data is that all points lie on a line, and the output of the problem is optimal weight of the edge that connect two points in a proximity graph. We can reduce the number of variables without affecting the optimal solution. Using this, we present a dynamic programming algorithm that computes the optimal weight in big O n squared time. If we use quadratic programming instead of our algorithm, then it takes nearly big O n cubed time. The problem is challenging even for one-dimensional data. For one-dimensional data, the problem can model the task of detecting change points and concept drift in a time series. Now we show that we can reduce the number of variables to obtain an optimal solution. We assume that input points are given in sorted order, and let J be an arbitrary index between I and K. And let A be the distance between Pi and Pj, and B be the distance between Pj and Pk. And W be the edge weight between Pi and Pk. We remove W by setting W to 0 and distribute the weight Wt to the other weights. Each Wij and Wjk increase of certain amount. This modification doesn't change Vi, Vj, and Vk. It means that the optimal solution is not affected by this modification. Therefore, for one-dimensional data, there is an optimal solution where only weights between consecutive points are non-zero. To simplify the notation, we set the I as distance between pi and pi plus 1, and wi as the weight between pi and pi plus 1. Q function is the proximity graph objective function for each choice of wi. And qi only consider p1 to pi. wi minus 1 depends on wi. It means that an optimal solution is determined by the optimal value of the last variable wn minus 1. Therefore, qn minus 1 is the final function to find wn minus 1 to minimize qn minus 1. Let Ri be the derivative of Qi with respect to Wi. Qi plus 1 depends on Wi to Wi plus 1. To constraint Wi plus 1, Qi plus 1 can be written by using Qi. If we know the Wi that minimizes the Qi, then we can get the Wi plus 1. For a given value of Wi plus 1 is greater than equal to 0, then we need to find the value of Wi that will minimize Qi plus 1. To find the minimum Wi, we take the derivative with respect to Wi. Then the minimum Wi occurs this value. Let Wi circle be Ri inverse 0. It means that Wi circle is a value that minimizes Qi. There are two cases to get the optimal weight of Wi. First case is when Wi circle is greater than or equal to 1. Since Ri is strictly increasing, this condition implies that Ri inverse psi I Wi plus 1 is greater than equal to 1. So we set Wi to this value. The second case is Wi circle is less than 1. Wi bow tie is a value between Wi circle and 1 that satisfies this equation. And there are also two cases depend on I minus Wi bow tie. The first case is Wi plus 1 is greater than equal to 1 minus Wi bow tie. If we replace Wi bow tie by a large value x, then x plus Ri x over x psi I increase beyond 1. Because Ri is strictly increasing, Wi plus 1 is already greater than equal to 1. So if we find a particular Wi that corresponds to this particular Wi plus 1, then it is satisfied the constraint. Therefore, we set Wi to this. The second case is Wi plus 1 is less than I minus Wi bow tie. So if we replace Wi bow tie by a value x, that makes x plus Rix over psi I is less than 1. The function is increasing, so we can use the ideal value because the ideal value doesn't satisfy the constraint. To satisfy the constraint, we set Wi to this value. We replace Wi to one of these two values under the constraint. Then we can get Qi plus 1 and Ri plus 1. Ri plus 1 is strictly increasing, continuous, and piecewise linear. To compute optimal weight, the optimal weight Wi is computed by Wi plus 1. Therefore, we need to get the optimal value Wn minus 1. So generally, we set Wi to max value of these two values by using Wi plus 1. Wi plus 1 is that already computed to satisfy the constraint. We construct the function Ri one by one. To compute Ri plus 1, we make use of explicit representation of Ri that we have already computed. Depending on Wi circle and the constraint, the number of pieces of Ri plus 1 may be twice the number of pieces of Ri. Therefore, it is unclear whether the number of linear pieces of Ri is bounded or polynomial in I. Because of that, we turn to an implicit representation of Ri. This representation is based on that there is a linear relationship between points on the graph of the function Ri and Ri plus 1. When case 1 and case A in case 2, Ri plus 1 is this. So Xi is the best choice of Wi plus 1 to minimize Qi plus 1. And Xi is the value the corresponding the best choice of Wi to minimize Qi plus 1. And Yi plus 1 is just the derivative of the Qi plus 1 at Wi plus 1. And Yi is Ri value at Wi. So we can express this relationship as a system of two equations. It can be written as matrix notation. When case B in case 2, we have Ri plus 1 like this. And we can get a matrix by doing similar to previous case. These three operations are used on the representation of a function Ri. For an operation on Ri, we progressively build I transformation matrix. To build these matrices, we need these three operations. Since arithmetic takes constant time, and it follows that the implicit representation of Ri support all three operations on Ri in bigger I time. Since operations on Ri take time bigger I, the total time to construct Rn minus 1 is bigger and square. Here is our conclusion of our work. We developed a dynamic programming algorithm to obtain an optimal solution to one-dimensional data. Our algorithm has two representations. The one is explicit representation and the other one is implicit representation. By using implicit representation, we compute an optimal weight in a bigger and square time.